to get a little bit more precise. Net force, huh? The net force exerted. And what else? And inversely proportional to the object's mass. Well, what's mass? How do we define mass, right? And 3, the third law, again, Newton's third law. This one people tend to remember better. For every action, what? Right, for every action, there is an equal and opposite reaction. Now, if you want to dig into the logic of these, there have been numerous articles written on these, like hundreds of pages have been written about the inadequacies and philosophical, vacuousness of these laws in some sense, because if you really look at them too critically, you'll start finding there's some, like, what is this really even saying, Like, what's an action? Because the thing is, when we apply the third law, there's going to be things which don't really seem like action. For example, here's an example of the third law. Right now I'm doing it. I'm pushing on this desk. My action on this desk, there's an equal and opposite reaction of the desk pushing back on me. See, depending on what's in your mind about action, would you see that as the third law? I mean, action to me, on the surface of things, of the word, it seems like there's motion involved, right? There's no motion involved here, right? So anyway, let me get past critiquing it. So what's the first law really say? So the second law here, there's a better way to say this, right? And the better way to say this is simply, the second law really simply says this: F net vector is equal to the mass times the acceleration. So if you have a mass m and you have a net force of F on it, right? Its mass times the acceleration is equal to that force. Another way to say that is the acceleration, right, is equal to the net force divided by the mass. So if I give you a force, if I give you all of the forces acting on a mass, then what? Then you can figure out the acceleration of that mass by dividing the net force by the mass, right? And we're going to do this, okay, in detail. A bunch of different cases. Now, then the question is, well, what are forces? What do you mean forces? Do you guys know common examples of forces? Example forces, yeah. Gravity, I heard gravity, that's a good one. What's the formula for that? F equals to, for us to start with, something like minus mg, let's say z hat. I mean, it depends on the coordinate systems you're using, but let me just say minus mg, let me say it this way, F equals to mg directed down, right? So if we're working in the xy coordinate system like we were doing projectile motion, what would the projectile motion? So we'd have, like, for example, 0 minus mg in the xy coordinate projectile system discussion we were having, right? So if the net force on the projectile, like this marker, oh, there was an action-reaction with a wall there. But if the net, if we're ignoring air friction, we just have, mass times acceleration is equal to 0 minus mg. And what happens there? So this is projectile motion. See what happens? So you can divide both sides by mass, right? And we get acceleration is equal to 0 minus g. This is huge. This is an amazing result. Do you understand this? This says the acceleration is independent of the mass. Now, commercials on TV are doing their level best to convince you otherwise, right? There is a law of commercial comedy that if a very fat person gets on a water slide, they go faster than the other people, right? This is a law of TV advertisement, but it is not true, ignoring friction and stuff, all right? In terms of just raw gravity, masses experience the same acceleration and consequently the same speed no matter what their mass is, right? Now this of course is assuming that the mass that we're talking about is inconsequential in comparison to the mass of the Earth, which is the source of this mysterious gravity, right? As we'll explain later in the course. But to a good approximation, near the surface of Earth, gravity is F equals to mg directed downward, right? Are there any other forces?
Electromagnetic?
Electromagnetic, yeah, E and M. E and M, we could talk about F equals to Q times the electric field plus Q times V cross B. This would be the Lorentz force. So if we had electric fields and magnetic fields, we can talk about that. That's next semester. You're getting ahead a little bit. We'll save that. It'll be a while. One we will talk about this semester, like spring force, right? You have spring force, F equals to minus kx. I'll just talk about it one-dimensionally. This is the spring force. What are other forces? Friction, that's a good one. There's the force of friction. We'll deal with that in examples soon. All right. Now the friction we typically deal with, we don't tend to solve. Well, I'll just say we'll deal with it soon. Let me not get into the details. One thing at a time. And then the other forces we tend to talk about in word problems here are just people applying forces, right? Like I just, find something I want to push and I, exert a force on it. We have examples like that, all right? Just a car, a person, whatever, donkey. Example, not you. So, but yeah, there are any number of different forces you can consider, right? So, all right, that's Newton's second law. Now, here's the thing. If we're going to, so basically we're going to say that we can tell if there's a force by there being an acceleration, right? So what happens if the acceleration is 0? You have F equals ma, right? The net force F equals ma. Suppose your net force is 0, what happens? The net force is 0, right? We have F equals to ma, which is equal to 0. So we have the equation A equals to 0. What's the solution? Can you solve it? This is a differential equation. You're like, I haven't had differential equations yet. You can't hold me to that. This one's not bad. We can all do this one. This is dv dt equals to 0. What's the solution of dv dt equals to 0? What's that mean? The velocity is what? Constant, right? So the solution to this is just that v at time t is equal to the initial velocity, v0. This is a fixed constant velocity, right? And then what's that equal to? So then we've got dr dt, right, is equal to v naught. And what's that tell us about r of t? What's r of t equal to? Integrating that, we get the initial position plus, t times the initial velocity. And I regret using subknots here because I've used the subknot in a different way over here. How should I fix this? Tell you what to do. I think I'm going to go back over here and I'm going to fix this by making these subknots stars. So I'm just going to make these stars, if you don't mind. for the sake of not confusing these two concepts, yeah? For the current discussion. So we'll make the star is just the, that describes the velocity or the acceleration or the position of the moving frame with respect to the fixed frame, all right? Are we good? Okay. So then what? So the acceleration is 0, right? So is the first law logically separate from the what? By the way, what is this right here? What kind of motion are we talking about? That's you say linear, right? That is in fact the parametric equations for a line. That is a linear path. If I was to graph it, right? It's a line. If I pick some time 0, we're at position r0, that's where t equals to 0, right? And then as time goes on, you go in the direction v naught, forever and ever, amen, yeah? So like this. It goes on and on. So if the force is 0, the second law logically says what? It says the motion's a line. So why do we need the first law? Calculus already says the motion's linear, right? Or it's at rest. When would it be at rest? How would you get at rest in this? V naught equal to what? 0, right? Then you'd be at rest. So it's either, so like a more classic statement of the first law is an object remains at rest. An object at rest remains at rest unless, an object at rest remains at rest or in a state of uniform rectilinear motion unless acted upon by an external force, right? We used to tell kids that. Google's dumbed it down to this, right? Uniform rectilinear motion, whatever that means. It means that. Okay, so the larger question though is we're formulating Newton's laws with respect to what? What is the canvas on which we're drawing this physics, right? The canvas which we're painting physics on is a frame of reference. Yeah? So is there one frame of reference? Well, no, right? There's infinitely many because you can start with one and take another one and move it, you know? And so how do we know that Newton's laws are going to be consistent in the different frames of reference, right? What are the rules for changing coordinates? Well, we derived them over here, right? So think about this. I have in my fixed frame of reference ma equals to 0. What would the acceleration be? And so like, you know, these are in my notation over here, this is a sub s, right? A sub s, a sub s, v sub s, r sub s, sub s, sub s, all sub s's, all right? So a sub s is equal to 0. What is a sub s bar? Right, it's equal to what? It's, I mean, I guess we have to solve for it, but it would be a sub s minus a sub star, right? In my current notation. So what's the problem here? Or what's the potential problem? If you're going to measure the force in the S-bar system, how would you do it? Equals what? Mass times the acceleration in the S-bar system, yeah? And what's that going to be equal to in this hypothetical situation we're considering at the moment? It's going to be equal to what? Minus m a star. So I said the net force is 0, right? But if the a sub star is non-zero, then the net force in the moving frame of reference isn't 0 anymore. Yeah? So if we want the net force to be 0 in one frame to imply the net force is 0 in another frame, what do we need to assume about these frames of reference? What has to be true about the A sub star? So we need A sub star equals to 0. Let me put a finer point on it in this way. If the A sub star was not 0, right? You'd have the situation, think about this. In the initial fixed frame of reference, the motion is along a line. In the other frame of reference, the motion's not along a line. It's around something else. A parabola, a circle, an ellipse, who knows, right? This is not what we want for our concept of coordinate system, right? Certainly our system, if you just intuitively think about it, right? If the motion's along a line with respect to one coordinate system, and you look at another moving coordinate system, you'd like for it to still be along a line, right? We're assuming what? I mean, that's not going to be true if that new moving coordinate system is accelerated, right? Accelerated frames of reference are really complicated. For example, take a child on a merry-go-round, right? He's just sitting on the horse, right? What's his motion? His motion is a fixed point. What's his motion with respect to the frame of reference the merry-go-round's sitting in? It's a circle, right? I'm assuming the horse doesn't move up and down, okay, for the sake of simplicity. But it's a circle, right? So you've gone from uniform rectilinear motion, which is a fixed point, to circular motion, right? Why is that happening? It's because the merry-go-round frame of reference is accelerated. So, listen, it's just simply this. Two frames of reference are said to be inertially related if the one is in a state of uniform rectilinear motion with respect to the other, which is just a fancy way of saying two frames of reference are inertially related if this r star is just equal to a constant vector plus t times the velocity. In other words, two frames of reference are inertially related if the acceleration of the moving frame is 0 in the initial frame. This is what we need for Newton's laws to make sense. We need to state them in one inertial frame of reference, and they're still going to be true in another inertial frame of reference. I gather I'm out of time, so I guess... Oh yeah, I'm sorry. Well, I ended calculus early today, so there was that. Do I get to account those? Do I move those top minutes over to here? Is that... I'll end early some other day, I promise.